So we've got a bunch of different carbons here. This would be considered an ether because we've got an oxygen directly bonded to two carbons. All right, so now let's go through and practice functional groups a little bit more and make a more complete list. So let's start with our more basic functional groups. What do we call a carbon-carbon single bond? Alkane. Carbon-carbon double? Alkene. Carbon-carbon triple? Alkyne. What do we call this guy? It looks a little bit funky. Yeah, so there's a handful of different names for this. You can call this an arene ring, a benzene ring, or a phenyl ring, or aromatic. Honestly, there's quite a few different names, but for right now, arene or benzene is adequate for describing this. These are all made up of just carbons and hydrogens. They're one of the more simple class of functional groups. Then we run into another type, and I'm going to use an R group here. So note up here that R equals some sort of alkane. Yep. So I'm going to box this off just so we don't get confused here. What if we have an alkane attached to a halogen, where X is our halogen? What do we call that? Alkyl halide. Let me slide this over. What if instead of a halogen, we've got an alkane bonded to an OH group? Alcohol. Some people get confused and they want to call this hydroxyl. I prefer that we stick with alcohol. Alcohol is a lot more descriptive for organic chemists. We've got another one here that was on our quiz yesterday where instead of an alcohol, we've got this SH. What would we call that? Thiol. Alcohols and thiols are similar, but still different. Why are they different? Yeah, alcohols can hydrogen bond, thiols cannot. Thiols, because of that, have a much higher vapor pressure. They're very, very, very stinky. They actually add thiols to natural gas. That way we can pick up a natural gas leak. We can pick it up in a part per million level. All right, we've got another one here where we've got R.
Wait, what did you say thiol can bond to? Besides alcohol?
Thiol cannot hydrogen bond, and so it's different than an alcohol in that regard. Whoops, that should only have one lone pair. All right, what do we call it if we've got an alkane bound to a nitrogen? An amine. One important thing with amines, too, is these hydrogens could also be replaced with another carbon. So, for example, what I mean by that is you could have R, NH, and then one of those hydrogens could be switched out with a different R group. Or you could have N, R, R. These are all considered amines. They're just different types of amines. What we call this first one is a primary amine. We call this one a secondary amine. And we call this one a tertiary amine. Whoops. They're all still considered amines in this case. All right. And then we've got a couple different ones. What if we've got an oxygen between two alkyl groups or alkanes? An ether. So this is an important one. What about if it's sulfur in between there? Sulfide. How many of you guys have heard the term disulfide too? So disulfides show up a lot in biochemistry. These are what link cysteine residues together on proteins. And so we may occasionally run into these as well. These are called disulfides. They provide a lot of structural support for proteins that have cysteine residues in them. All right, so these are a lot of our basic functional groups, but we're missing a whole bunch of them, right? We're missing the ones with the CO double bonds on them. So let's make a list of these. And this is something that... There we go. This is something that confuses a lot of people. They ask themselves, well, how is an alcohol different than a carboxylic acid? We want to be as descriptive as possible when we're talking about functional groups. So we have this whole variety of carbonyl functional groups, and they all contain a CO double bond on them. So our classic carbonyl functional group, I'll draw it out like this. And I'm going to put Y in parentheses. Y is just going to be some variable coming off of it. So let's label this as our carbonyl. And this is just a generic.
Did you label Y as R?
So in this case, if we label it as an R, it's going to be a ketone. We want to just label Y as being some variable. I'll show you guys what all those different variables can be. Yeah?
What are the dashes right there between the Y?
Oh, I'm just doing quotes.
Oh, okay.
Yeah, air quotes, right? So let's fill in this chart. And we'll fill in this Y variable up here, and then we'll include the name over here. So what if this Y group is a hydrogen? What would we call that? So let's swap out that Y for hydrogen. It's an aldehyde. And so what I'm going to do to show this is I'm going to do dash H, and then I'm going to put a squiggly line through it. That squiggly line means it's just attached where that Y used to be attached. Okay, what if it's attached to a carbon, and this carbon has other attachments going on? What would we call that? Ketone. Alternatively, we could just draw this as an R. So if you remember that R equals some sort of alkane, you can draw it like that. Clarify that. Okay. Next one, we've got an OH. Yeah, so we don't call this an alcohol now, we call it a carboxylic acid. We want to be super descriptive when we're talking about this. Carboxylic acids, by definition, are a lot more acidic than a normal alcohol, so we want to call them a carboxylic acid. Next one isn't an ester. Instead, we've got this OR group coming off. What do we call that? Or it's not an ether. I gave it away. It's an ester. This is one of my favorite functional groups. This is what gives bananas their strong smell, blueberries, strawberries. Most of the fruity smells we get are esters. Yep.
So all of these are functional groups just by the branch, or do you have to include the carbon double bonded to the oxygen?
You have to have it directly attached to a carbonyl CO double bond.
So if we were to identify a group, we would have to circle all of that.
Yeah, exactly. Yep. When we are identifying it, circle that CO double bond as well. We want to circle the entire thing. Okay, so we've got an ester. The next one looks a little bit different. Let me actually draw this out. What do we call it if that Y group is replaced with this chunk? Anhydride. And then after that, we've got our halogen. So I'll label this as our generic X. What do we call this? Yeah, we either call it an acyl or an acid halide. Both terminologies are used in your textbook. You'll see them used interchangeably. All right, and then the last one, but not least, is arguably the most important. What do we call it if there's a nitrogen directly attached to a CO double bond? Amide, or amide. And this is the stuff that holds together all of our proteins. Very important biomolecule. So like I said, try to get these either on flashcards or use the Quizlet app. Make sure you get these completely memorized. A few people get confused too, and they're like, well, why do we refer to something as a carbonyl? The analogy I like to make is calling something a carbonyl is like calling something a mammal, right? Yeah, it's a mammal, but what type of mammal is it? You can say, oh, specifically it's an ester. An ester is a type of carbonyl, just like a human being is a type of mammal. So both can be used, but we want to be as descriptive as possible, so we try to go with the ones on the right when we're naming them.
What's the difference between an ester and an anhydride?
Yeah, so let's compare that down here. So an ester would look like this. An anhydride would look like that. So an anhydride has a second carbonyl group coming off that other side. Yep, good question. All right, yeah?
And like the amide can also have an RR, or it's
Yeah,
also-
exactly. So just like with amines, you can have different types of amides as well.
Okay.
And you'll see that in your biochemistry classes as well. All right, so now let's go back to our molecular representations, which is where we kind of finished up yesterday. And we said that we have three main types of molecular representations. We've got molecular formula. Yeah, it tells you the overall weight and what atoms are in there, but it doesn't tell you the structure. The condensed structure is okay. We group similarities together. You can decipher the structure, but it's not as easy on the eyes. And then we've got our partially condensed structure on the right, where we actually draw out the bonds. And I said partially condensed structures are usually the preferred route. And then I said we also continue on, and we try to apply some time-saving techniques to these partially condensed structures. And so you guys saw this on your problem of the day, where anytime you see the terminus of a line or a kink in a line, you know that there's an implied carbon. All of the hydrogens are implied as well. And the last thing I said was that lone pairs are usually assumed, and then I've got an asterisk there, and we'll talk about that in a second. Yeah?
I had a question. So for what we did with that ring, 3 carbon ring for a pod,
Mhm.
you just drawn a triangle?
Yeah, if you just drew a triangle, it'd be assumed each one of the vertices on that triangle is a carbon, and each one of those carbons has 2 hydrogens off of it. That's a good point. All right, the lone pair thing. For the time being, I really, really, really recommend that you draw out lone pairs. It's better to draw them out. That way you don't confuse yourself, and I'll show you a few cases where it can be a little ambiguous if you omit them. So what we call this, when we draw it out this way, is a bond line formula. Or bond line structure. And this is far and away the most common way you'll see organic molecules written. It saves a significant amount of time. All right, so now let's go over some tips. So let's make a list of tips. And this is something I hope to pound into you guys this year. I really, really want you guys to get this down. The first one is to draw using approximate angles. What do I mean by that? That means if your hybrid orbital is an angle of 109.5, try to approximate 109.5. Don't have it be 20 degrees. That looks funky. It doesn't look right. So in this case, we normally will see zigzag notation. The one exception is if we have an alkyne, that carbon-carbon triple bond, then we don't show a zigzag. In fact, that looks funky because that should be linear. So we do see zigzag for everything but our alkynes. All right, number 2 is use dashes and wedges to show 3D layout. We're going to cover this a lot more later, but if you do have a 3-dimensional part of your molecule, try to represent that. If it's sticking out towards you, draw that as a wedge. If it's sticking into the board, draw it as a dash. All right, number 3 is arguably the most important one. I'm going to do it in all caps to show that I'm serious. Never have more than 4 bonds to a carbon. Chemists have a fancy name for this. We call it the Texas carbon. And if I see a Texas carbon on your paper, I'm going to draw a frowny face from here on out. I'm serious. In 3rd term, you'll see frowny faces on exams where I see a Texas carbon on there. People occasionally do it. Try to really, really remember that carbons can have 3 bonds to them or 4 bonds to them, but if I see that 5th bond, that's a Texas carbon, and you'll see a frowny face. Number 4 is include formal charges. And I'll show you guys an example of why formal charges are so important. All right, so let's think about this bond line formula. Right there. Let's draw out the actual 3-dimensional view of this. So what should this look like in 3 dimensions? Well, we've got a central carbon there, right? We've got a central carbon located right there. So let's start with that one. And then, if we think about it, we've got a CH3 group sticking up. That's that first one. We've got a CH3 group sticking out over to the right-hand side. And then on that left-hand side, we've got another CH3 group. And then we've got this hydrogen that's actually assumed sticking back. So we can't forget about the assumed hydrogen. So what's the shape of this molecule? Tetrahedral. Which means that all of the angles in here should be about 109.5, right? Yep.
Does that mean like carbon can't have like one bond, or sorry, one lone pair?
Yeah, so in this case, unless I draw a lone pair on there, it's assumed to be a hydrogen, right?
So it can't just have like one electron by itself?
No. Yeah, we'll cover that later. There are some types of reactions where you do see one electron. Those are called radical reactions. But for right now, let's assume that we're not dealing with radicals at all. Yep. All right, so let's compare this one to the one on the right. Oh. All right, so the one on the right I'm going to draw looks super similar. But this time that central carbon is a cation. It's missing an electron. So let's draw this in 3 dimensions. So we still have the central carbon. Well, even before we do that, we've got the central carbon. What's the geometry for that central carbon? What do you guys think? Raise your hand if you think it's going to be tetrahedral. What about trigonal planar? Why would it be trigonal planar?
Wait, no, it's tetrahedral.
We've only got 3 attached groups,
Three times.
which means it's going to be trigonal planar in this case. So it's a completely different structure. It is confusing because oftentimes people get stuck thinking, hey, this should be tetrahedral. But what's happening is if we're imagining viewing this on its side, so it's laying down like a pancake, we've got this empty p orbital sticking straight up and down. And this p orbital is vacant of electrons. So the one on the right is actually trigonal planar. And we call this a carbocation. These have completely different reactivities. They're very, very reactive molecules. So it is important, even though the one on the top left looks like the one on the top right, that formal charge changes everything about this molecule. Because of that positive charge, we don't have a hydrogen on that central carbon. Okay? So we're on number 5 now. One, two, three, 4. 5 is include lone pairs. Until you are an expert. I really prefer to see everybody draw lone pairs, and I'll show you guys why through another example. Let's say we've got a chemist, and the chemist draws this molecule. The nitrogen doesn't have any lone pairs drawn on it. Well, I've got a question. What if that nitrogen has 2 lone pairs? What would its formal charge be? It would be -1. So we would label this as negative. So the question is, does it have 2 lone pairs, or does it just have 1 lone pair on that nitrogen? If it only has 1 lone pair, what's the charge? +1. So lone pairs will help you to determine charge. So these are my tips and tricks with drawing bond line formulas. Really try to practice them. Go through sapling as much as possible with chapter 2. It's a great exercise. And then do as many problems from the book as possible. But let's do a couple practice problems together. Draw the following in bond line notation. All right, the first molecule is this one, where we've got a carbon on the end with 3 hydrogens. We've got a carbon here, triple bonded to a carbon, and another hydrogen. I'll give you guys a minute to draw that in bond line notation, but remember, you don't have to draw all of the hydrogens, or the carbons for that matter. Yep.
I don't want to get anything right, but since the triple bond is going to be linear, right? How do we indicate that moving that force, the carbon gets connected to other carbon to be straight on that too?
Mm-hmm. So the angle, you're saying between the carbon on the right and the carbon on the left should be 180, so you shouldn't have the zigzag notation.
So how do you indicate that how it's one carbon?
All right, do you guys want a hint?
Yes, please.
All right. So what we'll do is the carbon on the left, I'll just draw as a dot for right now. We don't have to include dots. We'll do a straight line over to a carbon with another dot. And then we've got this third carbon over here. These are triple bonded together, so we just show that as a triple bond. That would be the bond line notation for this molecule. So let's clean this up a little bit. Oop. I'm just going to redraw it and change colors. My handwriting is not getting better. So when you draw it like this, it's implied that there's a carbon there, and a carbon there. Right? So the carbon on the end has an assumed hydrogen. The carbon on the right has an assumed 3 hydrogens. Yep.
In some versions you guys also see that there's a space or a gap between lines. I mean, like, you know, if it's a single bond and there's a triple bond, you want those lines connected.
They should be connected to show that there is a bond between them.
Okay.
Yes. Yeah.
So there's no dots in your life?
No. If it helps you to draw dots for now, go for it. I won't penalize you for drawing dots. Yep. That's a good question. So you're saying, can you have something that looks like that? This is my personal pet peeve. The angle here should be 180 degrees. This shows it as approximately like 60-ish. Try to keep it straight because it's got that linear orientation. Yeah?
Isn't that like kind of like the problem of the day question?
The problem of the day question had a double bond in it. Yeah, so let's do a different one where there's a double bond in there.
So if you drew it kind of like that, or the double bond, could you do this one?
No, so let's try this one. Let's do carbon, carbon. Let's try this one in bond line notation. What angle should these 3 carbons have? If you're stuck, look at the central carbon and ask yourself, what's the hybridization for the central carbon? sp2. So this angle should be 120. sp2 is going to be trigonal planar. It should be about 120. So when we draw this, again, we want to approximate these angles. And we can draw it like that. Each one of these spots indicates a carbon with assumed hydrogens coming off of there. You don't have to draw the hydrogens if you don't want to. Yep.
What if you have like a hydrocarbon chain of just CH3 and they were installed in here?
Okay, so let's do that one. Whoop. Let me stick with the same color scheme. Got C, H, C, C, C. I won't have it go on past 4 carbons. Let's draw this one. So we've got 4 carbons. We go 1, 2, 3, 4, right? So in this case, we'd have a zigzag formation, and we don't have to draw in any of those hydrogens. All right, let's try another one. This one's going to look very, very similar. What if I drew this? Yeah, and this is one that tricks up a lot of people. I'm going to draw 2 options here. Which one's correct? How many carbons are in the one on the left? 3. We go 1, 2, 3. On the right, we have 4 carbons. So you do have to keep track of those carbons. So 1, 2, 3, that's incorrect. That doesn't work. versus 1, 2, 3, 4. That fourth carbon has a chlorine coming off of it, so we have to label any non-carbon or hydrogen atoms. So in this case, this would be the correct one. Yep. So you're saying at this point, can you write CH3? Yeah, you'll see that occasionally. You're welcome to draw it either way. Yeah. Yep.
I meant a hydrocarbon chain of CH, so that they were all linear. So would you just have 3 lines? Would you have to draw dots then?
So there is one weird example of that. You won't see it ever with all sp3 hybridized because it'll zigzag. It's 109.5.
But with SP hybridized.
So there's actually a theorized polymer. Or we could even just draw it like that. So let's try doing the bond line formula of this one. Yep. So the first one, if we look at it, this central carbon is sp. It's going to be linear. So we want our angles to be about 180 degrees, which means we want it to be straight. Versus this one's going to be sp2 on the bottom. That should have an approximate angle of 120 degrees. So we try to roughly represent the correct angles. So let's go down to this bottom one. How many of you guys think you got the bond line formula for this one? Ish, yeah? Okay, so we've got one triple bond on this side, and then a single bond, and then another triple bond. So we've got a carbon there, carbon there, carbon there, carbon there.
Wait, so we can't beat that?
So in this case, everything is sp hybridized. So they're all going to be 180 degrees. There's not going to be a zigzag. Anytime you see a triple bond, remember it's going to be linear. Double bonds and single bonds will zigzag. The one thing I will say that kind of irritates me when I see this on homeworks or exams is if somebody draws a molecule like this. The question is, does this one have 1, 2, 3, 4? Or does it have 1, 2, 3, 4, 5? Yeah, so in this case, if you actually overdraw that central line, it implies a fifth carbon. So in this case, this would not be the same as the one drawn above it. So do try to make sure that your triple bonds all stack up like a hamburger and that one doesn't shoot out too far. That can mean something else. All right? Yep.
And in instances like the one that's on the quiz, if there are 3 bonds instead of 4, you would draw the hydrogens.
If there are 3 bonds instead of 4.
Because on the quiz, the last one, you had carbon with just 1 hydrogen. So you would draw that 1 hydrogen.
Let me pull it up. I'm not sure what we're referring to. Like these ones?
Yeah.
So we hadn't covered bond line formula, so I drew everything out to avoid confusion. But now we know this time-saving technique that we can use to avoid having to draw all these C's and H's.
Okay.
Yeah.
So the center ones that have just the sp2.
Yeah, so let's even do this one in bond line formula. We could draw this one as 1, 2, 3, OH, right? And then lone pairs on there. Versus 1, 2, 3, SH with 2 lone pairs. We could draw them out either way. Yep.
How would you draw like methane?
So methane, people will normally draw as CH4. They won't just draw a dot. Otherwise, you could wonder, is that a period? Is that a stray dot? Nobody knows what it is. Yeah. Okay, so let's do one last one, and then I'm going to maybe start introducing a new topic. So we've got hydrogen, oxygen, carbon, double bond to oxygen, carbon, double bond to a carbon, and we've got a hydrogen, hydrogen, hydrogen. So I don't see any triple bonds. We shouldn't have any straight lines going through this. It's probably going to zigzag. That's one hint. Raise your hand once you think you've got the bond line structure drawn. All right, we'll give people another couple seconds here. You can check with your neighbor too if you want to compare. All right, so here's how I would draw it. I would draw it like this, right? So if we look at this, there should be 3 carbons. We've got a carbon there, and a carbon there. And then we've got the assumed hydrogens coming off of each of those carbons. Yep.
Do we have to include a hydrogen next to the oxygen, or can we miss it?
Yeah, so that's a great question. Anytime you have a non-carbon atom, you should draw the hydrogens coming off of it. If we don't include that hydrogen, then we have to wonder, does this oxygen have a charge on it? We don't know. So if it's a non-carbon atom, draw all of the hydrogens coming off. Yep.
Will there ever be a situation where we won't be able to identify the central element?
Not really. Once you practice this, it just becomes second nature. You don't even think about the carbons and hydrogens. You just know that they're there. Yeah. All right, so I'm going to introduce a new topic. Resonance. Most of you guys saw this on the problem of the day. Or it's not problem of the day, on sapling. The new problem of the day, you don't have to complete it tonight, but bring it to class tomorrow. It's going to be an in-class activity. We haven't had enough time to cover this in depth enough. But I wanted to present this introduction. And resonance is important because Lewis structures often don't adequately describe a molecule. And I'm going to show you guys an example of a Lewis structure here. So this oxygen has a negative charge. We've got a hydrogen coming off here. If we look at this, which bond is going to be shorter, the carbon-oxygen double bond or the carbon-oxygen single bond? Double bond. So if we look at the Lewis structure, we would say this one should be shorter, and this one should be longer. In fact, we can go through and we can even predict and say that a double bond in general is typically about 1.2 angstroms, so pretty short. A single bond is typically about 1.43 angstroms. But this is incorrect. The reality is, if we look at this, we've got an oxygen here, oxygen here. We've got delta positives here. These are actually the same length. And tomorrow what we're going to do is actually discuss why these two bonds are the same length and why we don't see the double bond on one and a single bond on the other. But this has to do with the idea of resonance delocalization of electrons. So I'll see you guys tomorrow. Make sure that you bring the problem of the day back with you. It's going to be an in-class activity.
Can we try it first?
Just a second. Let me shut this down.